Hi class, today we're going to talk about how to dig a hole. Remember when you were a little kid and you would go to the beach and try to dig a big hole in the sand? Or have you ever heard rumors about digging a hole to China? Did you ever think about how someone would actually do that? It would require a lot of strength and brain power. Maybe even help from billionaires all over the world. So let's talk about what would happen if you were to dig a hole through the earth and jump in it. Now let's go back to the basics. To dig a hole with a shovel, there's a lever mechanism that comes into play, which is a type of simple machine. But digging a hole might not be the best alternative. In fact, digging a hole of 1.20 meters deep or 0.91 meters wide can take up to 4 hours depending on your capacities. So hypothetically, digging a hole all the way through the earth would take one person around 4,850 years. This is where the jackhammer comes into play. This is a type of percussion drill that uses simple harmonic motion at a great speed to break through all sorts of materials, such as concrete and rocks. The jackhammer impacts the ground at an average of 3,000 hits per minute. But these vibrations also have negative impacts. First, they are very loud. They can produce up to 130 decibels, which is comparable to the sound emitted at the loudest rock concert ever recorded. Note that sound waves are mechanical waves, so transverse and longitudinal waves. Now, in order to dig a hole to the other side of the planet, we would need a gigantic jackhammer. You can only imagine how loud this would be. A solution for this would be to use dampers, but this can only limit the sound so much. Another problem is that this machine can cause harm to the user due to excessive vibration, meaning there would be a need for vibration dampening components. Our gigantic jackhammer would be equipped with peak technology active vibration control. Yes, just like we learned in class, to cancel a wave, a similar wave but with a phase shift of pi radians can be used. Therefore, we could equip our machinery with shakers that will transmit counter vibrations. Essentially, having waves out of phase leading to cancellation, and a decrease in sound. Let's do a problem and calculate where we should place shakers on our jackhammer so that it will transmit counter vibrations. Imagine our jackhammer is 10 meters high and a worker is standing on top of it percuting the ground with intense determination. As the hole is getting larger, the worker is getting fatigued because of the vibrations. These vibrations are reaching him at an amplitude of 0.02 meters. The jackhammer hits the ground 2,500 times per minute, and the wavelength of the shocks is 0.3 meters. If we can only place the shaker 2 meters from the ground, what would be the counter vibration equation? Well, here is how to solve the problem. First, let's take note of all the data given. The amplitude is equal to 0.02 meters. The frequency is equal to 2,500 Hz, therefore, the angular frequency is 15,708 Hz. The wavelength is 0.03 meters, and the wave number is 20.94 reciprocal meters. From that, we know that the initial transverse wave equation is this. Since the shakers are 2 meters from the point of impact, the path length difference is 2 meters. This means we can calculate the phase shift difference to be pi over 3 rads. To eliminate the maximum vibration, perfectly destructive interference between the vibrations is needed. Hence, the longitudinal wave of the shaker should be delayed by pi over 6. Thus, the equation of the counter vibrations is the following. Now, let's say that a person wants to travel from one end of the earth to another in the shortest amount of time possible. Let's assume that technology was developed enough to dig a hole from one side of the earth to the other, against insanely high temperatures and the air pressure found in the core of the earth. Once you jump in, you will experience a force pulling you from behind when you start reaching the other end. Thus, you will slow down until you change directions and start traveling again towards the other end. This motion will repeat itself until you stabilize, and become stuck at the Earth's core. Once you reach the middle of the Earth, gravity will not be considered to be a problem since it will be pulling you in all directions and your net force will be zero. Although, note that the net force is not zero because you experience no gravity, rather it is because the gravitational forces from all parts of the Earth would balance and cancel out. Then, there's another factor that would come into play in this hypothetical jump. While we don't notice on the Earth's surface, its interior is affected by serious tremors, meaning anyone who drills is aware of this problem. The problem in question is the Coriolis effect, which consists of these tremors caused by the rotation of the Earth on its own axis. The Coriolis force affects all bodies that are in motion within a rotating reference itself. This means that the person jumping through the tunnel from one end of the Earth to the other would be hurled from one side to the other throughout the course of the freefall. The only possible way for the person to escape the Coriolis effect would be if the hole was dug from the south to the North Pole, since the tunnel would be exactly on the axis of rotation of the Earth. In this instance, the rotating reference system would be the hole itself, thus no tremors would be observed inside of it. In fact, the gravity would pull you straight down. The reasoning behind the fact that a person jumping through the hypothetical hole would get hurled from one side to the next due to the Coriolis effect is the following. The planet rotates at a speed of around 1,000 miles per hour based on its surface level, but the Earth's insides need to move faster since they are at a closer distance to the core of the Earth than at its surface. This means that the person falling through the hole would have a greater speed than the hole itself as it rotates about the Earth's axis. Therefore, at around 1 kilometer into the freefall, the person would hit the side of the hole for the first time and continue to bounce from side to side from then on. Later on, once the person is approaching the middle of the Earth, their speed would be 1,500 miles per hour higher than the walls of the hole. Now, in a perfect situation, where the air resistance is negligible and the hole is dug from one pole to the other, jumping in the hole means you would be stuck in an eternal oscillating motion between the two poles. In fact, once you reach one pole, the gravitational pull of the opposite pole will drag you back across the hole, and so on forever. The only solution to this problem would be to have something retrieve you from one side of the hole, essentially dragging you out of the motion. As for sound itself, the deeper you would plunge in the tunnel, the speed of sound would change. In fact, since speed depends on the properties of the medium, and seeing as Earth's material becomes denser and more elastic as you delve towards the center, sound will travel faster. It's like how sound travels faster in solid materials than in air. Now, imagine you're making some noise as you fall, such as tapping or shouting on the tunnel walls. The sound will travel through the Earth, bouncing off the tunnel walls, and as you go deeper, it might even interact with the Earth's surface. But here's the catch, the Earth isn't a perfect conductor, so as you continue falling, the sound might weaken or even dissipate. It's like if you were in a large empty room, the sound will travel, but as it gets farther it becomes fainter. Moreover, depending on the dimensions of the hole, you might encounter resonance. This would happen when the hole's size matches certain frequencies of the sound, leading to enhanced amplitudes. Now keep in mind that this is a simplified view. The Earth's actual composition is much more complex than uniform. Moving on to a couple fun facts within this hypothetical situation. If two people were to stand on each side of the hole, and one of them tried to say something to the other, it would take 36 seconds for the sound to reach the other side in perfect circumstances. Clearly this is not the best communication technique, but it remains possible with the right conditions. Seeing as the hole through the planet would be of approximately 12,750 kilometers, this would explain the extensive time the emitted sound would take to travel through this hole. Now, in a theoretical situation where it would be possible to jump through the hole and land on the other side of the Earth, the time it would take to travel the entire length of the tunnel would be 42 minutes and 12 seconds. This freefall isn't for the faint of heart, but it's definitely more efficient than hours on end on a plane. That was it for today's lesson. Thank you for joining in. I expect to see you tomorrow with another crazy physics adventure. Bye.